Hello and welcome back, my fellow path integrators. Today, once again with a beautiful integral. As you can see, I have encountered this integral while trying to derive Kepler's first law from scratch, and I just wanted to share with you how I would solve this integral. So let's just jump right into it. So first thing I would do here is I would put the r squared into the numerator of the integrand. So it would be like 1 over r squared dr divided by the square root of a plus b over r minus c squared over r squared. And then I would already start to perform the first substitution, which will be to say, let's make it a bit bigger. So let's say our substitution will be psi is equal to 1 over r. This means that the derivative of psi with respect to r is equal to 1 minus 1 over r squared, and this leads to dr being minus d psi over psi squared. And now we can plug that into this integral here. So we just substitute 1 over r and 1 over r squared with psi and psi squared. So what we will get is, let's write that here, what we will get is the integral of psi minus the integral of psi squared divided by psi squared times d psi, and then the whole thing divided by the square root of a plus b psi minus c squared psi squared. Alright, now what I'm gonna do is I'm gonna rewrite this part here a little bit. So because this reminds me a little bit of a binomial formula, but in order to actually apply the binomial formula, what I'm gonna do is I'm gonna put the minus in front of the two terms. So it would be minus the integral. Let's put that integral a little bit down here. Minus the integral of d psi over the square root of a minus. And then we have c squared psi squared minus b psi. And that thing here we can extend to a binomial formula by adding 0. So what we do now is we have here c squared psi squared minus b psi, which is the same as c squared psi squared minus b psi plus, and now we add 0, b squared divided by 4c squared minus b squared divided by 4c squared. And as you can see, this here is equal to 0, so I just added 0. Now you may ask yourself, how did I know that I have to add exactly this? So how do I know I had to add exactly this? Well, I was trying around. So maybe you try around also a little bit how you can extend the whole thing to a binomial formula. And this, what we have here, so I'll mark it for a second, the whole term here, we can contract it to the binomial formula of c psi minus b over 2c squared and then minus b squared divided by 4c squared. So our integral changes to minus the integral of d psi divided by the square root of, and now we have a minus, we open the brackets, we have the first binomial bracket here, which is cx minus b2 divided by 2c squared, and then we subtract the b squared divided by 4c squared, and we make the square root closed. So what are we gonna do now? Well, this here is a constant, so we put that to this side here, and then what we get is minus the integral of d psi divided by the square root of, we have a minus, plus, because we have a minus minus, here I forgot a bracket, so we have a plus b squared divided by 4c squared, brackets close, and then minus the whole cx minus b divided by 2c in brackets squared. So now we already simplified our integral enormously. What we will do now is we will call this term here, we define that as a to simplify the whole thing a little bit. And then what we write is minus the integral of d psi divided by the square root of a minus c psi minus b divided by 2c and the whole thing squared. And now we can extract the square root of a. So what we do now is we say this here is equal to minus 1 over the square root of a times the integral of d psi divided by, and now since we extracted the square root of a, we have here a 1 minus cx minus b divided by 2c squared divided by this a. Okay, now we can go back to actual integration, and what we do now is we perform a little substitution once again. The substitution that we perform now is the following. We say that u of psi is equal to c times psi minus b over 2c divided by the square root of a. So the square root of this part here. And then, let's make that bracket a bit bigger. Then we will get that the derivative of du with respect to psi is just c divided by the square root of a. And this means that d psi is equal to the square root of a divided by c times du. And that's what we're plugging into the integral. And as you can see is, since we're plugging a square root of a in the numerator into the integral, and here we have a square root of a in the denominator, the two of them equal each other out. And the c here is a constant which we can extract out of the integral, so it will be just minus 1 over c as a constant factor in front of the integral. So the integral now looks like this. The square root of a's, they canceled each other out, so we only have minus 1 over c times the integral of du. Now we have du divided by 1, the square root of 1 minus u squared. And this looks quite easy to solve because all we need to do is to substitute the u with a cosine of phi. If you remember that the cosine squared of phi plus the sine squared of phi is equal to 1. This means that the cosine squared of phi, or in this case we'll do it differently, the sine squared of phi is equal to 1 minus the cosine squared of phi. And if we plug in cosine squared of phi for u squared, then we can easily solve this integral. So what are we going to do now? We're performing a substitution once again, but this time it's an easy substitution. I'll make that thing a bit smaller so we can squeeze the substitution in here. So we have, as a substitution, we say u is equal to cosine of phi. This means that du with respect the derivative with respect to phi is minus sine phi, which is cool to see because you see here we have a minus and here we have a minus, so we're getting rid of that minus, which is nice because that minus, that makes you a little bit nervous. But that's something that I would say. It made me nervous. When a sinus appears in front of an integral, I'm getting nervous. Like, did I make a mistake? I think you know what I mean. Alright, so we have here minus sine phi, and this means that du is equal to minus sine phi times d phi. Now we plug that into the integral, so we have minus 1 over c times the integral of minus sine phi d phi divided by the square root of 1 minus cosine squared of phi. And the cool thing is that this square root, the 1 minus cosine squared of phi, is sine of phi. So what we get here, first, the minus signs, they cancel each other out. So we are left with 1 over c times the integral of sine phi divided by sine phi, and of course with respect to phi. And this just means it's 1 over c times phi. Of course we can add a constant, but the constant in this case is not so important. Well, now we just plug in, so I'll just leave the constant out because you guys know that we need constants when integrating. Now we just plug in what we had for phi. So let's scroll up a little bit. What was phi? So we had u is cosine of phi, so phi is the inverse cosine of u. Okay, so we have here 1 over c times the arc cos of u. So now we plug in u. Let's go up again. Where do we have the u? U is c times psi, you can see it here. c times psi minus b over 2c divided by the square root of a. Alright, let's plug that in. So we have 1 over c times the arc cos of c times psi minus b over 2c divided by the square root of a. So if you remember, psi is 1 over r, so we have 1 over c times the arc cos of c over r minus b over 2c divided by the square root of a. And now we just need to plug in what the square root of a has been. So let's look up again. What was the square root of a? Oh, we have to go up quite a bit. Here we are. The square root, the a was defined as a plus small a plus b squared divided by 4c squared. So we just copy that part here and put it down here. Alright, so 1 over c is our final result now, so take care. 1 over c times arc cos of c over r minus b over 2c and the whole thing divided by the square root of what we had here. So now we close the brackets, make it look a bit more beautiful, and bam! This is our final result, the solution to the integral. It looks a bit complicated, but in one of my next videos I'm gonna show you how we can use this integral to actually derive Kepler's first law, so the law that all of the planets are moving in ellipses around the Sun. We can derive that law with this integral here and some physics, of course. We need some physics, but the only type of physics that we are going to need is the angular momentum and the conservation of energy, and that's quite simple, and of course Newton's law of gravitation. But those are quite simple things, quite simple concepts that we learn in school, and then we just need a little bit of calculus and we can derive one of the most fascinating results of empirical science of humankind. Alright, so far so good, I would say. It was a pleasure to have you with me in this video. I hope to see you again in the next one. And yes, leave a like if you like this video. Let me know in the comments if you would like to see the Kepler derivation. I really would like to do that. It's amazing. I can really tell you. Just stay tuned. Like, I'm gonna do that video for sure. Yes. So yeah, also subscribe to my channel. You know the thing. Subscribe, like, comment, but just do what you feel like doing. It was fun. See you in the next video, my fellow path integrator. Bye.